Okay. All right. So welcome back. Today is a little bit of a more fun recitation. We're going to be going over one little tiny topic that we need to go over. It'll take us about 15 minutes to finish this, if not less. And then we're going to do questions, test questions that you guys have sent. And then I also chose some random topics um, that I thought were fitting. So let's start. First, we're going to go over graphs and how we represent graphs in a computer. A lot of you already know this, but it's important to go over it because it's something you might be using in reading algorithms. So graphs are used for literally everything in computers. It's networking, it's databases, maps, whatever you want to save in computers. A lot of times they are graphs. So how do you actually save the graphs? How do you store the graphs? We're going to go over a couple of definitions, and we're going to see how you store them. So first, a graph is a collection of vertices and edges, right? Um, so we have graphs that are not connected and graphs that are connected. What is the definition of connected? Connected means I can get from any single vertex to every other vertex, right? So for every vertex, it means I can get from one to the other. So this graph is not connected. And this graph is connected because you can see from every vertex, I can get to every single vertex. All right, so let's just define that same thing that we just said. What is a non-directed graph? A non-directed graph is a paired tuple, I believe it's called, where it doesn't matter the order, such that V is the set of vertices, and E is the set of all the edges, right? So E is a set of edges, and how are the edges represented? It's represented as a set of two vertices. So if I have an edge from A to E, that means I will have A and E within my group E. All right. Um, so the elements of E are called just edges. Okay, now we have it's a little bit confusing, but usually when you see circular pairs, it means that it is a directed graph, right? Because that means the order matters, right? So E is where the edge comes out from, and the W is where it goes to. So it's the origin and the destination, right? So in a lot of places in computer science, you just write circle brackets instead of squiggly brackets as just a convenience thing. And you have to understand from the context um, if it's really a directed graph or non-directed graph. And they just write circle. I prefer to just always write the correct one. So if it's non-directed, I'll use the squiggly, and if it's directed, I'll use the circle.
Undirected means it can go either way, right?
Exactly. It means that there's no direction to the edges, right? Here, there's no direction. Does it go from E to A, from A to E? It doesn't matter. There's just a edge from A to E. All right, so for this example, how is this represented mathematically? The group of V is the group of vertices, and E is the group of edges. As you'll notice here, it's in circle brackets, but it should be in squiggly brackets, which is a little bit more formal. Now, directed graph, what we talked about kind of up in the air. But now let's define it formally. So a non-directed graph means that every single edge has a direction, right? It has an origin and like an origin vertex and also a destination, right? So here, for example, the edge FA is from F to A. There is no edge from A to F. We don't have such an edge.
If we did, what would it look like?
You'd have two separate edges, two arrows. All right. So now what we talked about connectivity in a non-directed graph. In a directed graph, what is connectivity? Or we say you can get from every vertex to every vertex. So here, as you can tell, it's a really bad picture. I'm really sorry about that. But imagine all these have directions. Okay. So now, if we want a directed graph to be connected, we need a path from every single vertex to every single vertex. right? It's a little bit more difficult in a directed graph because you need more of the edges. Okay? Now, there's a different definition that's not only connectivity, there's connected well, I guess, is what you could call it. Connected well is that there isn't actually uh, an edge from every vertex to every vertex. There isn't a path from every vertex to every vertex. But if all the edges were non-directed, then you could get from every vertex to every vertex. So let's say for this example, you can tell, like, let's say if this was pointing that way, this edge was pointing that way, you can get from B to, let's call this C, but you can't get from C to B, right? So it's not connected, but it's a graph that is not well connected, but is connected, means if I turn all of them into non-directed, then it would be a connected graph.
So from the point the top right, you could get to any other point, but because it's directed,
Because it's directed, we can. So that would be something that's it's not well connected, right? Because you can't get from every verse to every vertex, but you could if it was non-directed. And if it was, you could get from every vertex to every vertex in this graph, what would it be?
What?
If you could get from every vertex to every vertex, what would it be called?
Connected.
Connected, yeah, it would be connected. It would be connected, but in non-directed, in directed graphs, it's well connected. I'll have to look up the actual definition, but it's kasher tev is.
So there isn't such thing as connected.
There is.
We have two different types of connected in a direct graph.
Yeah. In directed, you have either fully connected, it's connected well, that means from every vertex to every vertex. And not connected well, but still connected means that if I turned it into non-directed, it would be connected. Okay. All right, so now how do we write this mathematically, a directed graph? So it's the same thing as before, just now our edges have an origin and a destination. Let's say A, E, right? It goes from A to E, not from E to A. So therefore we have a pair of A and E. Let's just see how that looks. Let's say B and F. We have an edge from B to F, an edge from B to C, right? From B to F and from B to C. We don't have the other way around. Now it matters what order those edges are. Okay, so how are we going to save that? That was great mathematically, but you don't want to save something like this in a computer. It's a waste of space. It's not very efficient. So we have two main ways that we're going to store them. We have an adjacency matrix and an adjacency list. I guess we'll go over both of them, but first, just a couple of questions. What are the values of the input, right? Runtime, we calculate it relative to the input, to the size of the input, right?
That means input.
Okay, that is input, exactly. So we need to define what is the size of the input in order to calculate runtime and complexity, right? So let's define that size of V is O of M, the size of E is O is equal M. Okay, now which runtime is better, O of N to the third power or O of M to the square?
It depends on the size of each.
Depends on the size of each, but more specifically.
You can have more edges than vertices, but not
Exactly.
Yeah, you can have the other way around, but
you can't have the other way around, exactly. It depends on whether or not we have a lot of edges, right? You can have a graph that has no edges. If it has no edges, obviously we prefer O of M squared because it's just nothing, constant time. But if we have a lot of edges, what's the most amount of edges we could have? Such as, you see, if we have not very many edges,
directed or not directed?
non-directed. Let's say for this example, we have only a couple graphs, so we prefer to have O of M squared runtime. But let's say for this graph, which is, it's called a full graph or click, if you've heard that term, it's where we have an edge from every single vertex to every single vertex. So how many edges do we have if we have N?
And times N is minus 1, was it?
Nope. N choose 2. Why N choose 2 if we have V equals N, then E for a full graph equals N choose 2. Why? Because if you take any two vertices, you have an edge between them. And how many different possibilities do you have to take two different edges? And choose 2. So in a full graph, in a clique, we have n choose 2 edges. So therefore, n choose 2 is big O of n squared. So in worst case, we have m is O of n squared. Right? So if it's a full graph,
So
then O of m squared equals to what? Equals m to the 4th power. 1 second. M to the 4th power. Is that understood? Yeah, what do you want to say?
yeah, I thought that was that reason.
Oh, okay. So you got it right. You just said it a bit
Yeah,
different.
I said n minus one, but it's going to be like two.
Divided by 2.
But
Okay.
because it's n minus one divided by two, it's if we have this, then the max the m we can have is of order n to the 4.
You get n to the 4th would be the worst case. Then we prefer O of n to the 3rd power. Okay. So it depends on whether we have a lot of edges or not a lot of edges, right? So runtime is usually represented as with these two parameters, the size of the amount of vertices and the amount of edges, right? So what would linear time be in a specific graph? Linear time is O of V plus E. This would be linear time because it's linear in the size of the input, which is V plus E. Is that understood? Okay. So exactly what I said, it would be linear time. In a connected graph, a runtime size of O of n plus m equals m. Why does it equal m?
Because
It's connected.
if it's connected, it's 2m. Like it's at least 2m, no?
Well, not 2m, but if it's connected, that means I have at least n minus 1 edges, right? If I have n different vertices, in order for this graph to be connected, I need at least n minus 1 edges. It's something that we proved in discrete mathematics, but if you want to, we can prove it after class. But just take it as a fact for now. So if the graph is connected, O of n plus m is basically O of 2n minus 1, at least. Therefore, it is O of, therefore, n is smaller than m, so therefore it's O of n. All right, now adjacency matrix. Let's go through this quickly. What does this represent? This is how we're going to represent a directed graph in an adjacency matrix. So we have a table, a matrix of size of n times n. Each cell represents, do we have an edge from the row to the column? So do we have an edge from B to A? We do, because there's one there. Do we have an edge from B to D? No, we don't have one. And if you look in our graph already, from B to A we have an edge, and from B to D we don't have an edge. Okay? So this is how we represent an adjacency matrix. Now, if we have a non-directed graph, then how are we going to represent an adjacency matrix? Notice that now, because they don't have a direction, the matrix is symmetric on the diagonal, right? If we have an edge from 2 to 1, it means we also have an edge from 1 to 2, because we don't care about the direction. So a lot of times in questions, they'll describe a problem with an adjacency matrix on a non-directed graph, and they'll say we're only going to use the upper half. You can ignore the lower half, because we only need to use half. You don't always have to update both sides because it's symmetric. Okay? Now, a little bit of questions. What's the runtime to decide if we have some sort of edge in the graph? If I want to decide, if I want to see if I have U and V, if I have that edge, how long will that take me?
Do we know that?
O of 1. I'm just going to look it up in the table. I'm going to go, so let's say it's 3 and 2. You go 3, 2. I do have an edge, O of 1. Okay? What about memory? N squared, exactly. So therefore, if n is a lot smaller than n, if we have not so many edges, our matrix will be mostly zeros. If it's mostly zeros, it's not so efficient. Also, something that we do a lot of times in algorithms is that we want to check all the neighbors of a specific vertex, right? How long would that take us here? Check all the neighbors.
N.
n, exactly, because we have to look through either the whole row or the whole column. Every time there's a 1, we add it to like the neighbors, right? But O of n is not very good because, like we said, if we don't have so many edges, it could be only has one neighbor. It would be O of 1. Now we have O of n, which isn't so good. So that's why we have what's called the adjacency list. And it's better if you want to find neighbors, right? If you a neighbor is certain. A neighbor is if I have, like you want to define it. If there's an edge between two vertices, they're neighbors. Okay. All right. So for a directed graph, what does an adjacency list look like? We have basically an array of all our edges, of all our vertices. Sorry. For everyone, we have a linked list. We keep a linked list of all of its neighbors. Okay. So for 0, you can see that we have 4 and 2 that are its neighbors. So we add for 0, 2, and 4. Now, also note that here how we're saving it is for every vertex, we're saving the linked list its neighbors that are outside, that come out from it, that it has an edge from it to the neighbor, right? But you can technically save it the other way around if it's better for you. If you want to save for 2 that 0 is its neighbor. So whatever you prefer, usually we just do it this way just to be, just to have a unified and thing and not be confused. But technically, for like every single vertex, we just save the linked list of its neighbors that we have an edge from the vertex to that same that other neighbor.
I mean, for directed graphs, it's better to save it depending from.
For directed graphs,
I mean, this is directed now.
it's directed. It's a
So it's better to save it from who goes to full now.
From who goes to who? You mean like for 0?
Goes to 2, so you
Exactly, it's better. It's better for most algorithms. So if you want to do it backwards, then you have to look up backwards. But I'm just saying you could do it, but it's not. You're right. Just ignore what I said. You shouldn't do it. You should do it this way. It's more efficient. Okay, now for a non-directed graph. Now for every edge, for 2, we have to add 5 to link this as a neighbor, and for 5, we have to add 2. So really, for every edge, now we're adding two different nodes into link lists, right? So for 2, we're going to save 5, and for 5, we're going to save 2. Okay. Now, if I want to add an edge, let's say 1, 4, I'll have to add to this linked list 4, and I'll have to add to this linked list 1. Okay. All right. What's the size of the representation? N. Not n squared. This is O of n. You're right. What about this? How many of these do we have?
The amount of edges.
N. The amount of edges, but times 2, because for each edge we're adding it twice, right? So 2 times the amount of edges. So therefore, it's O of n times n.
Wait, size in like space or size?
Yeah, space. So yeah. So the space is O of n plus O of 2 times n, which is O of n. All right. And now also you can see how long does it take us to find all the neighbors of a certain. Let's say I give you the vertex 4. How long does it take to find all the neighbors? It's not technically in worst case it's O of n. Like it could be neighbors with everybody. But we know that if it has, let's say, k neighbors, it's O of k. So if we don't have so many edges, then it's a better runtime. Now this is not so important, but we're gonna do it anyways. Okay, so what is interval graphs? Also, this is important if there's jobs in general. And a lot of the code questions, they have interval questions, so this can help. Basically, you're not given a graph, you're given these intervals. Okay? And when you're given these intervals, it's not so easy to analyze them with the computer because you're just given 2 numbers of the range, and you have to loop. Let's say if I want to find which intervals intersect with C. So you'd have to like draw a line here and see that B and A both intersect C. But that's easy for us to do now when it's all drawn out nicely, but a computer can't do that. You'd have to loop through every single interval. So instead of that, we can turn it into an interval graph. What is an interval graph? We have basically each interval is its own vertex, and we have an edge between 2 vertices if they intersect. So between C and B, we'll have an edge because there's a point where they intersect. So B and C will have an edge, and so too B and A will have an edge. They also intersect, and also C and A will have an edge between them. But C and E, or sorry, not C and E, but A and E won't have an edge between them because they don't intersect. And then if we save it in an adjacency list, it's very easy. If I want to check, let's say, for G, who intersects G, I just check its neighbors, right? Which is just F. So I know that just F is intersecting with G. Okay? It's an important side note. We're not going to do any questions with it. But it's a very cool concept. It does help a lot with job interviews and stuff. It comes up. So
In what way do you mean? Oh, that's awesome.
Hi,
In what way do you mean it comes up in job interviews?
like job interviews, a lot of times they'll ask you leak code questions. And in some of these leak code questions, they ask you, like, I got actually the question. It wasn't with interval graphs, but it was intervals. In one of my interviews, they asked me, like, given a list of timestamps, like when people log in and log out of work, they asked, like, keep a list of how many people at each hour like are on call, right? So I have to keep a whole running list, and I'd have to work with those, like analyze those intervals. So there's like questions that come up in job interviews that have to do with intervals. Sometimes turning it into a graph is more helpful, but it's side note. Okay. All right. So now I'm sure you're tired of this already. And I think we're just gonna skip it. I was gonna go through all the different things and do a little like runtime quiz and stuff. But I think we're just gonna skip to the questions because we only have an hour. All right, and I am gonna be doing a shot Kabbalah, like office hours, in the last week, like the week of the test. I'm gonna be doing it in Hebrew, and I'm just gonna be going over questions and topics and so on and so forth. You're all welcome. I'll send an update of when it's gonna be. Probably Tuesday, but I'm not sure yet. All right, so this is a question we already did.
Next week?
No, next week, 2 weeks.
Right.
The week of the test.
Yeah.
Okay. So this is the question that Adva sent me, dynamic programming question. So we'll read the question together. Then I'll give you guys like 5 minutes to solve it, to try, and then we'll solve it together, okay? All right, so every natural number n we can represent as a sum of other numbers that are squares of some natural number. So for example, the number 6 we can represent with 1 squared, 1 squared, 1 squared, 1 squared, 1 squared, 6 times equals 6. So we can present 6 with a bunch of squares. But in a more efficient way to do it would be 1 squared plus 1 squared plus 2 squared, which then also equals 6, and we need less numbers. So the claim that we can represent any number with a certain amount of natural numbers squared is true for every single n. Why? Because we can always just represent it with ones, right?
Yeah.
So we can always represent it. The question is how many? What's the minimum amount we can do it with? So the problem that they're asking us, we have the input is a number n, and the output is a representation of n with the minimal amount of squares. So for this example would be 2, 1, 1, right? 2 squared, 1 squared, 1 squared. So your input is this, and your output is the minimum amount. Well, the actual representation. So the problem is you can solve it with dynamic programming. So we have A, B, and C. A is you have to first do the recursive formula, and you have to define all of the parameters and just solve it according to the order of operations that we saw in the dynamic programming one. And you also can note that here they didn't ask for the naive way, so you can just skip right to the recursive. So take a couple minutes, try and do the recursive one. If you finish, you can try and turn it into dynamic programming. Good enough.
Just do it.
Yeah, that's all. Also, you should note that you don't have to prove it formally, but we'll try and prove it formally because that's what that asked me. I could prove it formally. So,
We can try to use words, but like the problem is when you use words, you never know like is that good enough? Is that a good
hmm.
explanation? Like this
Okay,
is the
okay,
problem.
all right.
If you can give like also tips to explain it in words, then also like everything welcomes. Just
Hmm.
kind of like a guideline would really help of what you expect to see. I know it's not firm and it changes, but a guideline will really help.
All right, okay. So everyone take 5 minutes
Thank
to solve it, and then we'll solve it together.
thank you.
Also, if you finish this, there's more questions. I've uploaded the presentation to the Lambda, so you can just continue onward and just keep on solving questions if you finish.
אדריאל,
כן,
אה,
כן,
העלו את הזום האחרון, כאילו הייתה הרצאה שבוע שעבר בזום,
של איילת או
והוא...
של משה?
לא, של משה,
של משה, אני לא
שהוא לא
יודע.
העלה עדיין לזום,
כנראה שהוא לא ידע.
ללמדה. לא, אתה יכול רגע, יש מצב אתה רק בודק לי שנייה, שאם לא אני אשלח לו מייל, אם יש לך
סבבה.
גישה, כי לי אין גישה ללמדה. אה, של האנגלית.
Okay. So you should be finishing up. If not, it's all good. We'll go over it together. Kind of just like if you couldn't solve it, it's also totally fine. Um, dynamic programming, just the slides.
אוקיי, אני אשלח לו מייל, תודה.
Bekif. All right, so let's do it together. Okay. So we need first our recursive formula. Now, for dynamic programming, for the recursive formula, it is divide and conquer, right? Which means we just take our bigger problem and we try and make the input smaller, but an input that is an input to the same problem, right? Try and make it smaller. So remember from the recitation we did, like, let's say for the backpack, for the knapsack problem, we made it smaller on two different axes. Here we're just making it smaller on one axis. It's a little bit simpler. So how are we going to solve it? First, what are we going to make smaller?
One.
N. Exactly. We're going to make the number itself smaller at every recursive call. Okay? So let's define our recursive formula given some sort of k. What does it equal? Remember, you need a base case.
Base case
Is 1. Okay. So I'm going to do base case equals 0. Technically, you could also do 1. You could also do 1. But it depends if the natural numbers include 0 or not.
Yeah.
But you want to start from the lowest one.
Yes.
So let's say if it includes 0, let's just start from 0. If it doesn't include 0, you can start from 1. Let's say if k equals 0, then what does it equal? 0. Then understood why? Our base case, we're trying to represent the number 0. We need 0 numbers to do it, right? Okay, now what's the rest of the case? Otherwise? Otherwise what?
Base.
You think we have 2 cases? Okay.
I don't know.
Okay.
I
So
didn't
let's just
first.
let's just notice something that will help us solve it. What's the biggest? Let's say we're trying to represent k, right? What's the biggest number that a squared could be equal k?
The square root of
The square root of k. It's the biggest number. It's the square root of k. It's the biggest one. So we're gonna do the min, right? Because we want the minimum of all these different recursive calls. If I'm trying to represent k with squares of numbers, the biggest one is square root of k. Why? Because if I take, let's say, square root of k plus 1 and square that, I'll get k plus 1, which is already bigger than k, and it doesn't help me.
Right. You're saying the biggest
Exactly.
number, not the biggest amount of numbers.
Exactly, the biggest number, exactly. So what we're going to do is each time we're going to take, right, one of these numbers that we square, and subtract it from k and call it recursively. But we want a number that returns the minimal, right? The minimal amount of numbers needed to represent it. So we're going to do minimum of some sort of I in between square root of k and what?
and 0.
And 0.
You.
Well, in this case, 1, because 0 doesn't help you. Of we're going to call f of k
Minus I.
minus I squared, right? Because we're representing it with I squared. And
Plus
and
1.
Plus 1.
Oh, in the
Okay.
recursive, no?
You can do it either or.
It doesn't matter if I put it outside or inside? The
No,
minimum?
no, it doesn't matter.
Also, you need
Because
the
I'm returning the minimum of all these. If I put it inside, it's the same as just adding 1 at the end.
also you need
Okay.
category of being less than. I know it can be less than k, but it can be not a natural number. So you can have to throw those out.
Oh yeah, if I is a natural number. Yeah. I is a natural number between 1 and square root of k. Okay? Now what are we doing here? We're basically making the input smaller every time. We're taking the minimum of all these different i's, because right, we're trying to represent k equals some sort of a1 squared plus a2 squared plus whatever plus let's call it t squared. Right? With all these different numbers that are squared. So we want to minimize this t. We want to minimize the amount of numbers that are here. Okay, so if in each recursive call, we're adding 1 for our element, for our I, plus, and then we're going to recursively call it on k minus I squared. Because if we have, let's say, we take A1, this is our first one that we took, and it's in the minimal, let's say this is the best solution we can get to. So we also know that k minus A1 squared equals the rest of this, right? Plus whatever, plus AT squared. So basically what we're doing is we're saying, okay, let's try all the different options from 1 until square root of k. So we're trying all these options. Take the minimum I, which is going to be any of these, really. We're going to recursively call it on each one of these, and also a bunch of other ones, but the other ones don't get us an optimal solution. And if we call it on any one of these ones, then it'll be minimal, and we'll basically add 1 to it, and then call it recursively on k minus that same element squared. Y plus 1 because we're doing because we're adding that one element, the I, into it.
It's
all right. I see a lot of confused faces, so let's do this again. We want to calculate the minimum. This is just the problem, right? The minimum amount of elements that are, if each one is squared, it equals the sum of them equals k, right? We want to minimize the amount of numbers. We can do any like numbers in the end equal k, but we want to minimize them. Okay, so how are we going to do that? We're going to recursively call on all the different options. What are the different options? Between 1 and square root of k. Those are all the different options that squared can be equal to. Like any one of these specific elements is at most square root of k, and at least 1. So we're going to try on all the different options. We're going to recursively call on all the different options. And for each one of those options, what we're going to do is we're going to take that same I. We're going to recursively call it, right, divide and conquer. We're trying to make the input smaller. So we're going to subtract I squared from k. So now we're trying to find some sort of this different sum, which is now smaller, and different, like the minimum amount of elements that now equal to that new sum. Okay, so we're recursively calling it and making it smaller, 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 and every time we take an element, we add 1, because at the end it's going to return the amount of elements. Okay? Questions?
I was on the right track, but you don't put enough time between.
It's not an easy problem, and if you haven't done the dynamic programming homework yet, it might be a little bit more difficult. Okay, so this is our solution, and also in the end, we also want that if we take a number, no, this is good. The second we get to k, we just return it, and then we return the minimum of all those recursive calls. Okay? So first off, now what's the runtime of this?
This is
Okay. Use that.
n squared.
Isn't it n squared?
Every time we have k, right? We have first n, and we have from 1 until square root of n elements.
So it's k. Just
So but k changes every time, so it's a bit difficult to do it, but it's at least we have big O. Let's pretend that each time it's from 1 to square root of n. So we have square root of n different calls, right? For each one, it splits up square root of n times. And we stop once, at most if everything is just 1, 1, 1, 1, 1. So therefore it would be, this you have to do a recursive function t of n equals square root of n t of n minus 1 plus O of whatever. This wasn't in the question. Plus square root of n. This wasn't in the question. But technically this is the recursive formula.
no, it can't be. It has to be the t has to be like the sort root has to be inside of t, right?
The square root has to be inside of t?
Yeah, because you're doing n minus 1 work.
Oh, you're right.
So you're doing
Right, it's square root of t of n.
and the work you're
Because
doing
each
is
time it is at most.
the work you're doing.
No, wait, no. It's no, I stand by what I said. It's n minus 1 because at worst case, what's the worst case? That we took I equals 1. If we took I equals 1, it just subtracts 1 from the sum, and therefore we call it recursively on that same thing minus 1. Whatever, it's not important. I don't know why I asked the runtime.
Yeah.
It's not.
They asked.
They asked the runtime?
No, that's the right time on the
On the
second
dynamic-
on the
On
dynamic one.
programming. On the
And then
dynamic-
it's more easier. And then it's easier, yeah.
on the dynamic programming. No, I did it for the recursive. I'm right now still on the recursive part.
Recursive. Good
Yeah.
dynamic model.
Dynamic is then using memory to make this better. Right now it's bad runtime. Okay,
Isn't
so now after we explained the recursive formula, now they do ask to explain. Well, you have to also explain each parameter in the recursive function. So what is k?
Okay, it's the number we want to.
We want to represent with the rest of the squares, right? Okay. So and then the last thing we have to do is explain the output and the correctness of the formula. So if we call f of,
What do they mean by correct? Doesn't that just mean we have to prove?
this is our answer. So what does that mean, correctness? So in most cases you have to prove it. Here they ask just to explain it. That's what I was asking about. Technically, to prove it, you need to prove two things, right? Sorry, Sammy. There's no way I'm going to be able to erase all this.
Oh, do you want me to do it?
No, it's all
I'll do it.
you can try. So in order to explain correctness, well, first proving correctness. Proving correctness, you have two things you need to prove, right? You need to prove validity, that the solution is achievable, that you can get to this like you can, the function that return, like our function on k returns a valid solution. And the second thing you have to prove is that it's optimal. So this is always the formula for proving dynamic programming solutions. One, f of k is valid, and two, f of k is optimal, right? Optimal means that it's the minimal amount of numbers needed to represent it. Okay, so you need to prove those two things. So, to explain correctness, is already, you don't have to prove it. You just have to explain in words, like as if you would explain to me why your solution works.
I don't think I have the physical skill of being able to do that.
Well, also, you didn't have enough time to think about this problem, and you didn't practice enough dynamic programming. It's kind of like I just fell on you with this kind of complicated problem. But in order to explain correctness, let's say for this example, you just have to explain why your recursive formula returns the optimal amount. So let's say for our recursive formula, right? Let's say, basically, we're doing 1 plus the minimum. We're trying all the possible options of square roots that could be, right, that are possible. If let's assume for the sake of contradiction, that f of k is represented with another series of numbers that we didn't catch in our thing, in our formula. If we didn't catch them, it doesn't make sense because Ri tries all the different options up until square root of k. So that can't be possible. So I kind of did the sake of contradiction, but really what you need to explain is that we try all the possible options and we return the minimum of them. So therefore, our recursive formula is optimal because we tried all the options. If you want to be really exact, you can say, assume for the point of contradiction that there exists a solution we didn't cover, but covered all the solutions. We covered all the options, so therefore it's optimal. Okay? It's basically just explaining. It's a lot easier. It's a lot easier, and we're a lot more lenient when we check it. If you explain, if you're in the general direction, like we'll give you the points. If we see that you know what you're talking about, then we'll give you the points. There's no like formula for it. Like in proving there's a formula. If you don't do it according to that, we'll take off points. But in explaining, if you just explain to me, you try all the possible options, therefore it'll return the optimal solution, that's enough. Adva, did I answer your question? Adva?
Wait, I was mute. I'm sorry. Yes, you did.
Okay,
It
okay,
just
amazing. All
it
right.
just like you said, like it's sometimes when you explain in words, like it's easier to get like confused and then like you will check my test and you will be like, what is she talking about? So
Exactly.
and also most of the question you need to prove that like this is from
Exactly.
2021. Since
Exactly.
2022, you don't have these kind of things. So
Yeah, most questions you have to prove, especially dynamic programming. Sorry, not most questions. Restart. If if it's dynamic programming or greedy algorithms or divide and conquer algorithms, you're gonna have to prove it. Most chances, unless it's a little bit complicated or too long to do it in the time frame of the test. But usually we'll ask you to prove it. Explaining is like just to make it a little bit easier. We think the question is a bit too hard, so we'll make it a bit easier by just asking you to explain correctness. Now let's say we want to prove this. So first off, is this mostly understood?
Well,
Okay. Then we try all the possible options. So now let's prove correctness. So how do we prove correctness? Induction, right? So we want to prove it
wait,
in
correctness
induction.
is like what is
Um,
correction? Correctness, valid or optimal?
this is correctness.
Ah, okay, okay, thank you.
Correct. Well, technically, correctness of the whole algorithm is that it's also valid and optimal,
Oh, okay.
technically,
yeah. Yeah.
I think. Because if the algorithm is correct, it means it returns the minimum amount of.
Yeah, but you can
The algorithm is correct, but you're right. This means that it returns something correct. Like,
No,
that's why I call it valid. It's
valid,
like,
valid is that it returns the correct answer. Optimal is that
That's like in
the
movie
minimal
does.
one.
exactly, does.
So-
Exactly. It's like in both of those dumb questions that else.
Yeah, exactly.
All right, so we're doing induction on K, right? And we have to prove the two things, right? So we have to prove what? Prove for every K what? We want to prove validity and what? Optimality or whatever. Sounds like what? Optimalness. Someone look it up. Anyways, so what's our base case?
0.
Yeah, base is K equals 0. And now we have to prove for 0 that it's valid. And taking 0, like representing it with no numbers where it is valid. And also proving optimality, right? That we want to prove that there's no way to get that lower down. You can't represent it with less than 0 things. So those both are just trivial. You can just write in a couple words. And now what's our step? We're gonna assume, right? Assume for every K smaller than K and prove for K. What are we assuming? Validity and optimality. We're going to do them both in one. You could technically divide it up into 2 separate inductions, but we're just going to do it in one because it's a bit easier, okay? Now, how do we do this? First, let's start with correctness, with validity. How do we prove that it's valid? Always in proofs of dynamic programming and divide and conquer, what you do is you always go back one recursive call, because it's recursive, right? So you go back one recursive call. The input becomes smaller, K becomes smaller, and then we can use the induction hypothesis to then prove that it's correct on that smaller thing, and then we just go back to our original problem. So let's first validity. Let I star be the min number from our formula. So the min from I from root of K and 1, so on and so forth, right? From our formula. So I is the minimum from this choice. Okay? And now what do we do with I? Now let's take I away, right? This is always how the proofs go in recursive formulas. Let's subtract I. Let's go back a recursive call. So now our recursive call is f of k equals 1 plus f of k minus I star squared, right? So recursive call, because this is basically the minimum of all those different ones. All right, so now what can we do? Now, by the induction hypothesis, what do we know about this? It's valid, right? F of k minus I star squared is valid, and therefore also our fk is valid. So basically, it's like almost trivial, like it's to prove it, because you just go back a recursive call and you say that's valid. So then if I add this new square, if I know that this solution sums up to k minus I star squared, then f of k, by adding that I star squared, we'll get to k and it'll be a valid solution. Okay? Now optimality. How are we going to solve this? Same way. We're going to go back one recursive call, and then we're going to use the induction hypothesis, so on and so forth. I just want to do a full one. I know it's a little bit tedious, but I just want to do a full one with you guys, because sometimes, no one shows you how to do it, and then you never know how to do it. Okay. So now, how do you prove optimality? It's the same formula. You assume, for the sake of contradiction, that something else is more optimal, and then get to contradiction. Okay? Assume, for the sake of contradiction, that there exists that f of k is not optimal. Therefore, there exists now I'm just doing the solution that is optimal. This is our new solution. Optimal solution such that t is strictly smaller than f of k. It's just a little bit tedious, but you guys understood what I did here. Just assume for the sake of contradiction that it's not optimal. Therefore, there exists some other representation that is optimal. And if this one is optimal, that means the amount of elements, t, is smaller than our f of k. Because it's optimal, right? If ours is not optimal, there exists one that is less, right? So now what are we going to do? This, we're going to get to a contradiction. Okay? So we're going to just, let's just look at one of the specific elements. We'll subtract it from k. Right? I'm running out of space. Okay.
Can we do it like the valid part and like let I square be the one for f not I square, I like tag be the one for f tag, and then do the
For
same
what?
trick? Can we do the same trick like the valid? The valid
For the valid, where we go back one, that's what we're going to do.
okay.
We're gonna do it, but just it's a bit more complicated because you have to prove it's optimal. So we have to assume for the sake of contradiction that there exists some other one that is optimal. So take this k minus b1 squared is equal to what? Equal to b2 squared plus b3 squared plus bt squared. And what do we know about our algorithm? That if we call our algorithm on k minus b1 squared by the induction hypothesis, it's optimal. Right? Because we assumed that it's optimal for every k smaller than k. And this is strictly smaller than k. So therefore, by the induction hypothesis, f of k minus b1 squared is optimal, right? Therefore, if it's optimal, it has to be greater than t minus 1. Right? Because we're representing t different elements. Oh, sorry, not greater, smaller. Because we're trying to show that this is optimal. So it's smaller than t minus 1. Because it could be this solution or it could be less than. Because we know ours is optimal. Therefore, f of k is smaller than f of k minus b1 squared plus 1, right? Because just by definition. And then we know that this is smaller or equal to t minus 1 plus 1 t contradiction. And we are done. Guess I'll just go through it quickly. This is how also all proofs on dynamic programming are going to be. We do with usually induction on some sort of parameter. We're going to, in different questions, this is a different parameter, but we're just going to be induction on something. You prove for every single k, you have to prove both validity and optimality. Sometimes it's easier doing two separate inductions, but here we're doing it together. The base is just your base case. It's really just according to your recursive formula. Then the step. We're going to assume for every k minus smaller than k, we're going to prove for k. And we have to prove validity and optimality. Validity is just go one backwards, go one recursive call before. And we know by the induction hypothesis, it is valid. So let's add back our I star. And now we have a valid solution, therefore fk is valid. And the same thing with also optimality. Same thing, let's go back a recursive call. And then let's prove. But in order to prove optimality, the general formula we use is to assume for the sake of contradiction, it's not optimal. So we assume it's not optimal, therefore there exists something else that is optimal. And therefore, if it's optimal, it means it's strictly smaller than our solution. Because it's optimal, our solution is not optimal, let's assume. So therefore, it's strictly smaller. If it was a maximal problem, it would be strictly greater. But either way, it's the same thing. And then once we have that, you take the solution, you go one recursive call backwards, right? We take our solution, go one recursive call backwards, and we know that that one recursive call backwards is, this has to be more optimal than this one. Because this is one, just by definition, this one could include this function, this one, right? This one takes the minimum, so therefore it's obviously smaller equal to the one before it, because it's this bi squared is either minimal or not, and then using our induction hypothesis, we get that it's smaller equal to that our solution is at least t. If not, it's more optimal than t. Which is a contradiction that t is more optimal in our solution. Okay, so that's just the general formula. You just assume for the sake of contradiction that there exists something else that is more optimal, and then go back one recursive call, use the induction hypothesis, and then just prove, and then just get to a contradiction. Okay? Because in the previous recursive call, when you go back one, you can use induction hypothesis to say that one's optimal. So it was important for me to just show you one full proof. If they asked you to prove it, this is how you would prove it in a test. Yes, questions.
Why do we care about proving the optimality of a recursive formula that we're not even gonna like really ever
We're
use?
not even going to use it, and then we're using dynamic programming, right?
Yeah, so why do we care about
So the
proving that?
dynamic programming is based on the recursive formula. If you prove correctness of the
But what's guaranteeing that the dynamic, like, for example, the dynamic, I forgot the phrase. Yeah, we've got a dynamic program. Yeah. What's to say that the dynamic programming of a different recursive formula isn't better, like wouldn't end up being better than the dynamic programming of this recursive formula? Like, what guarantees that
Well, usually
that the optimality holds?
Okay, so when you do dynamic programming, you base it off of your recursive formula.
Right.
You're right. If I did some dynamic programming solution that wasn't based off of this, instead of it's based off of some different recursive formula, then I didn't prove anything for the dynamic programming. But when you solve dynamic programming problems, you want this recursive formula to be the base for your dynamic programming solution. And if you really base it off of this, if this is correct, then the correctness of the dynamic programming,
But what
it just comes
what I'm
instantly.
asking is what underlies that allows us to just assume that for every single recursive formula.
That allows us to assume that we can, if we prove this, that we can then jump to correctness of dynamic programming solutions. If you do it wrong, it's not correct. There's no assumption that says for every recursive formula, if you prove it, then some dynamic programming solution is also going to be correct. It's only the dynamic programming solution. Technically, we're skipping on a little bit of the proof, like that we're not making you guys do, which is just from this show that they prove that it's the dynamic programming is based off of this, therefore it's also correct. You're not really proving that, but I think you have to do that proof too. Does that make more sense? That if you have your dynamic programming solution, you have to say, we prove that this is true. And now let's prove that if this is true, then our dynamic programming is also true. But most of the time, it's just relatively simple because we'll see also in the dynamic programming we're going to do right now, that it's really, it's the same. It's really based off of it. So let's do that quickly. If you want, we can talk more about it after the lesson. I thought I would get through more problems. Okay, so how is the dynamic programming solution going to look? Remember, you have to show the data structure, right? You have to describe the data structure, the size of it, what every cell represents, how we're going to fill it up, so on and so forth. So what's our dynamic programming solution going to be? Well, what?
We just do an array.
An array, exactly. Also, general rule is usually if you have one parameter, you need a 1D, one-dimensional array. If you have two parameters, you probably need two. Okay, so now how are we going to fill it up? Well, first, what's our base case?
0.
0, right? So we're going to start here. When k equals 0, then it is 0. What's the size of this? N, exactly. Very good, Sammy. And now, what does a cell represent? What does cell 3 represent?
The number of
The recursive formula, exactly.
Yeah.
Basically just the recursive formula, right? 3 is basically just f of 3. All right, and now how do we fill up our array?
Plugging it into the formula.
Exactly. We're plugging into the formula, but you have to explain. You take the minimum of all the previous i's, right? So if we're on 1, it's just between 1 and 1. So you take the minimum of f of 1 minus 1. So it's just based off of this one, right? So it'd be 1 plus 0. And then 2 would be the same thing, between 1 and square root of 2. So it's only 1. So you do 2 minus 1, which is just 1. And so on and so forth. You'd fill up the whole cell based off of all of the cells before it, because you don't know which I you're going to need, right? Could be that I is based off of just the first cell.
Wait, no, 2 is 2.
2 is 2. Oh, yeah, you're right. You're right. Sorry, my bad. Wait, no.
Yeah, it is.
Yeah, you're right. 2 is 2. You're right. Because it increases by 1 every time. Exactly, you're right. And then for each one, you have to check all the valid i's from the natural numbers. So therefore, we have to check all those valid i's and check if they exist in the cell, in our if we calculated them, if they exist here. So let's say for like a cell 10, let's say, we basically have to check 1, right? 1 cell back, 2 cells back, and 3 cells back, right? But that's squared because we're checking on that squared. So for this one, we'd have to check 3 squared. So 10 minus 3 squared, which would be this first cell. So it would be 1 plus the first cell, which is either for 3 it would be just 2, 1 plus this, or 2 squared and 10 minus 4. So that would be 6. Let's say in the 6th cell we have 4. So that would be 5. So either 2 or 5 or 1. You go 1 back. And let's say we have 1 back, it's equal to 5, let's say. And then it would be equal to 6, and it would take the minimum out of all those. So the minimum would be 2, and it would put that in. So you have to calculate it based off of the previous cells. And when you explain your dynamic programming solution, you have to explain that, how each cell is calculated on the previous cells. What were you asking, Thomas?
So we have to check all the previous cells.
Not all the previous cells, but specific ones, right? Because we're on cell 10. We have between 1 and square root of 10, which is we're on down to 3. So between 1 and 3, we have to check all those i's. What does it mean we check those i's? We check the cell of k minus that same I squared. So we have 1, 2, and 3. We check 10 minus 3 squared, right? So that's the first cell. Because 10 minus 9 would be the first cell. Then we check that plus 1. And then we basically take the minimum of checking all those options of 1, 2, and 3. In this example, the minimum is really taking 3 squared. And adding that, 1 squared. And then we can represent 10 with 1 squared and 3 squared. Okay? All right.
Yeah, but you have to subtract, right?
You have to what?
You have to like go through each cell and subtract like the maximum. So you go to 3, you see it's 9, so you take out 9 and then you check for 1.
In 3?
Like first you go to 3 and you
Yeah, same thing we'd fill this up to until 10. You fill it like cell by cell.
And then you check how much the value is of the highest one.
Exactly, the minimum one, not the highest one.
Or the minimum.
The minimum of all these cells that you can get to.
Yeah, but
Okay.
always like the biggest number is going to be the best. No.
The biggest number is going to be this, not always.
Sure.
Maybe you're not always. Not always. Not always. There are cases where it's not.
Sure.
Okay, so we also have to do the runtime. What's the runtime of this? How are we going to fill this up? We have n cells to fill up, so it's n times. How much does each cell take us? We have at most square root of n options to check, right?
Yes.
It would be n times square root of n. This is our runtime. And you'll see if you look at the solution, I put it also on the it's just, you can also do it this way, where if you want to do it, each one is square root of k, and then analyze it a little bit, get a tighter bound, but it's the same bound in the end. And then also, I'm not going to go through it, but technically then we can also go, and if we want to give the actual elements that we chose, the actual values that we use to represent that same n, you can go backwards, like we did in the recitation. I'm not going to go through it. You can read the answer. It's pretty straightforward. You just, I guess I am going to go through it. Just for each cell, if the value here is, let's say, x, then you want to go backwards and check for a cell that has x minus 1. If that cell has x minus 1, we know that this cell took from that cell. But also such that it's n minus some sort of square. So you basically go to this cell, you go backwards, minus 1 squared. Right, so minus 1. Check that if that's x minus 1. Then you go to this one, you do x minus 2 squared, so minus 4. And if it's x minus 1, you know that there's a valid solution that uses this plus 2 squared. Okay? So you just go backwards, checking every squared if it equals x minus 1, and then that's how you can do that. All right, so let's do a couple more questions. I'm actually going to skip this one because it's a bit long. It's on ABL. It's a good question, different rotations and stuff. But let's do this one and this one. Okay, I put these two because they're a lot of people were very confused in the homework. I don't know about you guys, but with the Israeli ones, a lot of people were confused on the question where you had to prove that some sorting algorithm didn't exist, right? There was a thing where you have n divided by 10 rows and 10 columns. Does that algorithm that sorts that, does it exist?
So you might I don't remember.
Don't remember either.
But I remember.
I got Constantine to help me with that one.
It's a hard one, so that's why I wanted to go over a few of these ones. Also, I chose the harder questions because I was like the easier questions you guys can like read the answer and figure it out. Let's do the harder ones. I'm sorry that I chose
Okay.
hard ones. All right, so let's do this one. This is actually something else. They don't say prove or disprove. They give you a clue. They say prove. So you don't have to prove that such an algorithm exists. Prove that there exists an algorithm that builds from any n elements that aren't necessarily different from the range of 1 to n. It builds an AVL tree in the time of O of n. So prove that such an algorithm exists.
Isn't the algorithm just going to the middle and just
That's what it's sorted. Let's say it's sorted. We have n elements. We don't know if they're sorted.
Yeah, but we don't care if they're sorted. It's asking us to make an AVL, and AVL doesn't have to be.
It's not sorted. It's in a search tree. AVL.
It's a search tree.
It's a search tree. Yeah. AVL is a binary search tree, but it's a balanced binary search tree, right? We have a binary search tree where we have, let's say, 5, and then 3, and 7, 6, 9. This is, let's say, an AVL tree because it's balanced, right? It has to be a binary search tree, so I have to be able
Does it
to
have like the numbers?
exactly. And the balance factor is the
That'll be more than
left subtree minus the height of the right subtree, right?
So,
So in this case, it would be like -1, be this balance factor. This one's one smaller than this one, and this one would be 0. This one would be 0, 0, 0.
Right, it can't be more than one.
Exactly. And if we would insert something to here, we'd have to fix it with rotations. And that would be doing this. We're not doing this because it'll take us a bit of time. But let's do this algorithm, this part, because it's a bit shorter.
so
Yeah, 1 points.
you have an array, let's say, of n numbers that aren't sorted, and you need to have a sorted tree that's balanced by the end.
Exactly. We have n elements. We have n elements, right? These aren't sorted. And at the end, we need an AVL tree. So the trick here is we learned an algorithm in the recitation that builds an AVL tree once it's sorted in O of n, right? You just always take the middle as the root. You just do subarrays and you keep on taking. So we just need to get it sorted. How do we get it sorted?
Select.
Select doesn't sort it.
Yeah, but
How do we get it sorted? Look,
So. Wait.
we're sorted as n log n. We need it in O of n time.
Then, yeah.
Prove that such an algorithm exists. Come on, guys.
I mean,
Is it like
wait, what are you expecting? It has to be less than n log n.
Maybe
worst case O of n?
Worst case O of n.
Okay.
Worst case O of n. I'm gonna give you a big clue. I'm just gonna do a little circle right here. What does it say? From the range of 1 to n.
Oh, so it's the
Yeah.
whatever it's called.
What is it called?
Ah,
Come on, tell me.
so no.
Bucket sort?
Count sort.
What?
We're gonna do count sort.
Yeah.
Yeah, where you have the range. When you know the range, you can sort it
So
It's
it's
O
plus
of-
k.
n plus k, but k, the range here is n, so it's just 2n, and then it would be O of n. So your algorithm is 2 stages. And you write a little bit more on the answer on the test, like just explain a little bit more and analyze the runtime. But your first step is just count sort, and then 2, build AVL from like merged from count sort is when we know that each element is between 1 and n. We can sort it in a smart way. That we can basically count the amount of times that 1 appears in our array, count the amount of times that 2 appears in the array. If you go back to the recitation on sortings, it's there, there's animations, it's pretty understood.
So to answer this question, you need to have remembered from the lecture that there's an algorithm that if we have a sorted array,
It builds an AVL tree in O of n. Yes.
yeah.
Once you have that, you just do count
So
sort.
if you didn't remember that from the lecture, you
Yeah.
lost like 15 points.
Yes.
Oh my god.
That's why most of practicing for this test, you need to know the material and then it's practicing questions. But it's more important, in my opinion, it's more important to knowing the material. Practicing questions is also important. You need to know how to use what you learn, but
better to learn the material than to practice the questions.
I do both at the same time. I'd go over a subject and then I do a question on that subject just to make sure I understood the subject.
You don't have enough time to cover the subject.
But you need to cover all the subjects here. All right. So this question too. Prove that there doesn't exist an algorithm that, given a set of n elements from the natural numbers, builds in the time of, it's missing here, but O of n, 2, 3 true, right? That contains those elements. We have to disprove. In the previous one, we proved, so we just showed an algorithm. This one we have to disprove. So we learned two different ways. We learned two different ways to disprove that an algorithm exists. What's the first one?
Show this if what we can found this
That this is, what do you mean minimum?
it's like it's not algorithm and we prove that this is gonna be
Oh, if you like prove an algorithm is like that the minimum runtime is a certain amount, then you can't do it in less than that. Okay. We sort of did learn how to do that, but not what I was like going for. Also, usually we don't give questions like that. We have to prove a lower bound on the algorithm. Usually. But what I was going for is the lower bound of sorting. It's the first one, right? If you can take a certain amount of n elements and then sort them less than n log n, that's a contradiction to the lower bound in comparison sorts, right? So that's our first way of doing it. The second way that we saw in one of the recitations, that there was, you could get the minimum in O of 1 from n elements, which obviously is not possible, because in order to get the minimum, you have to look through all of the elements. So it's not possible to get an O of 1. And that's also a contradiction. So those are the two main ways that we saw to prove something doesn't exist. Contradiction to some sort of operation that doesn't make sense in that runtime. Like if you have to go through all n elements and check them, it can't be less than O of n. Or you get a contradiction to the lower bound of comparison sorts. Which one should we try for here? What are the two options I said? Just one of them. Which one? Yeah, let's try. The answer really is, let's get a contradiction with the lower bound of comparison sorts. How are we going to do that?
We'll assuming, how do you say it?
For the
We'll
sake of
assume
contradiction.
there is one.
Yeah, exactly.
Yeah, we're assuming contradiction.
Assume that there is one. Okay, and then what?
We can traverse it in O of n and get a sorted array.
Yeah.
Exactly. So what's the answer? It has to be a little bit more formal than what we just said, but we're going to assume that that algorithm exists. Let's say we can build a 2-3 tree in O of n, right? And a 2-3 tree, each node has either one element or two elements, right? So that's for the root. It's just it's a search tree with just sometimes it has two elements, right? It's just a search tree. So let's assume for the sake of contradiction such an algorithm exists that it takes n different elements and builds a 2-3 tree in O of n time. So building the tree would be O of n time. And once we have the tree, we can do an in-order traversal. And we know that any search tree, well, we proved it for binary search trees, but it's for any search tree. If you do an in-order traversal, you print the elements in a sorted manner. So if we do, this one is 1, run the algorithm, and 2, step 2 is do a DFS in order, which prints in sorted manner. Sorted order.
That was just the timing.
I know it's like it's
There must be just like a single button to press,
yeah.
and then it stops doing it.
Yeah. So these are our two steps. The first step is just use the algorithm, build an O of n, and then we can use DFS to sort it. And this is a contradiction. Why is it a contradiction? Contra.
What was the question, sorry?
The question was prove that there's no algorithm that can do this. Take n elements. Takes n elements, right? We have our, let's say if it's an array or whatever, n elements. Turns it into a B tree, the O of n. Right? So we need to disprove that such an algorithm exists. So how do we do that? Let's assume it exists, and then let's use it to sort our n elements in less than O of n time, n log n time. We know this is O of n, and therefore the subtotal is O of n, which is a contradiction to the lower bound of comparison sorts. You see a confused face.
Oh, right, because we proved that you can't have a comparison sort.
Exactly. That's what we proved from the lecture.
And again.
In n log n, exactly. And that's important to know that if you're trying to prove something doesn't exist, usually it's going to be this. Usually it's going to be assume it does exist, then use it to sort something in less than n log n, which is a contradiction. Okay? All right, sometimes like in the question that was in the homework with the n divided by 10 rows and n 10 columns, you had to do some pre-computations here before you can use the algorithm. Here you just take n elements. But what if it said it can take a sorted array and then turn it into a B tree? You'd have to do that first computation in order to use the algorithm. Right? In the homework, it was take n divided by 10 rows and n divided by 10 columns. And then you have to somehow take your n elements and divide it up into n divided by 10 rows and 10 columns. So you have to do that pre-computation, and then you can use this to get to a contradiction.
I don't know if they checked my homework yet. The way I did it is I said that you need a omega log amount of the permutations
Okay.
to do it,
Okay.
and that's how you know if it's possible or not. Because if you have 10 rows of n divided by 10, you have n factorial divided by 10 factorial.
Okay, yeah, that's another way of doing it. Okay, so I have a question.
Adriel, we lost the camera. If you're doing
We lost the camera. Thank you. I have a question. If you guys want to do one quick question, or you guys are done.
Yeah, we can do one more probably.
Okay. If someone wants to leave, feel free. I'm not gonna.
Can I ask just a little general question about like the last one we did? If
Yeah.
you don't ask me to do a solution recovery, do you need to mention something about it?
If you
In
don't
the
ask
dynamic
what?
programming. Like in these questions that I brought to you specifically, they ask to address the part of the solution recovery. If you don't do it, you just say to me, solve it using dynamic algorithm, dynamic
You're saying the
program.
dynamic programming
Do I
question?
need to address the part of solution recovery? Do you want me to write something about it in general?
You're talking
'Cause I
about
have
the
a
dynamic
recipe.
programming solution?
Yeah, because like I have a recipe on how to answer it, so I need to know
Okay.
what to write on this part.
So what are you asking?
Okay, when I do a question in dynamic programming, not like
Yeah.
this one, they just say solve it using dynamic programming.
Yes.
Do I need to address the part of solution recovery? Like say for
Oh,
example,
solution
and
recovery
if we
only?
don't
No,
want to
if they don't ask for it, you don't need to.
I don't need to mention anything because some
No.
people write on their test, if you don't want to use the solution recovery, you can like
You
make
can do it with less space. Yeah.
the
Do it with less
space
space.
complexity
If you want
smaller.
to, it's more proper to write it that way, because if they don't write that you need to do the solution recovery or the retrieval or whatever it's called, if you don't need
If
to
you
do
don't
that,
expect it.
then you can do it in less space, usually.
Yeah.
Thinking about
She means like, let's say in our dynamic solution where we had it in a sometimes let's say in the class we
Like we
have
did in the lecture.
like,
Exactly, we
for a
did in the
lecture,
lecture.
exactly,
Yeah,
we
we did in
have
the
a
lecture
matrix.
classic one. Yeah.
And each cell is based off of the row above it, right? So therefore, you only need to keep 2 rows technically. If you want to then go backwards and give the group of the choices that we made, like
right.
then you need the whole matrix. But if not, you just need 2 rows. So she's saying if it's not specified that you need to give the actual choices, if you just need to give the end result, then do you have to do the better solution? And it's better to do the better solution. It's more optimal space-wise. But probably I wouldn't take off points for it. Maybe like a couple, like maybe like 1 or 2. But it's not.
Thank you.
Yeah. All right. So I guess we'll finish today. This is a really cool question. I thought we go over it, but it's okay if you want to. I uploaded the whole presentation. It doesn't always have the answers, but it says the date up here. And if you have the actual date, you can just look up the answers on the Google Drive. All right. If there are any more questions? No? Okay. All right. So I'll see you guys next week for
Oh, we're not
reading
gonna do it?
algorithms. And the last one. That's the last recitation. All right.
Semester is ending.
Congrats, guys.
Oh,
Wait,
so
why
that's-
no? Why not doing it?
Why not doing
You're
what?
done?
It's